Okay. Okay, so let's go back. Okay, so we were saying that the question would only give you, for example, the question would give you this. But the question would also say balance in acidic. And so what you would need to do then is you would, oh, come on. Okay, you would add hydrogen ion as a reactant and add water as a product. And then it's all the steps we did before. That's the, oh, son of a, okay, that's the only change. Hopefully you can still read that. I meant to make it out. Okay. Okay, so then you start with this. So you might have to do the oxidation numbers for every single one and then find the ones that change. Now see, this is given. So they're leaving out spectator ions. So we can see that this changed. And this changed. So we start by writing the manganese is a +7. Okay, so let's go through the process. Let's work this out. We would not have this. And we wouldn't know this yet. And we wouldn't know this yet. Okay, so we would know we have a +7 and a +2. We want to aim for a +2 on both sides. So we've got +7, -5. That would give us a +2 on this side and a +2 on this side. So we're good. We see the electrons are here. And that fits our definition. Reduction is gain. And then we know the oxidizing agent goes with the rig, and specifically, it's our reactant here. So notice this always goes with the rig. So the oxidizing agent is specifically the Mn+7. Let's do the same with the chloride. And I'll also give you some time to copy it down. So the chlorine is diatomic. This is a molecule. We're going to have to leave this as a molecule, but we have to go back and put this 2 in ourselves because we would need 2 chloride to make the diatomic. So we would see that there's a -2 on this side. And remember, this was a 0. So we need a -2 on both sides. So if we have 2 electrons on this side, we have a -2 on this side and a -2 on this side. The electrons are being lost, and so that as our oxidation is lost. The oxidation is lost matches with the reducing agent, which is specifically the chloride. So now we need to balance the electrons. So if we multiply this half reaction by 2, we would get 10 electrons. If we multiply this half reaction by 5, we would get 10 electrons. So then we do the distributive property. And then all the reactants stay on the reactant side. All the products stay on the product side. And we have 10 electrons, 10 electrons. So I'll give you some time to copy that down. Does anyone need the little annotation on still? So this is what we have so far. Then we go back to our original question. We don't show the electrons, they cancel. We have to go back and find our manganese 7, the chloride. We throw in the H+, we'll have to figure that out in a second here. And then we have the number for the chlorine diatomic. The manganese +2 is by itself, and then we have the water. So now we need to work on balancing the oxygens and the water. Okay, so you've got 2 times 4. That's how we get our 8 oxygens. And then the only source of oxygens on this side is the water. So if we put an 8 in front of the water, then we would have 8 oxygens on this side, and we'd have 8 oxygens on this side. So we see on our product side, we have 8 times 2, that would be 16 hydrogens. So we can go back and we can fix our hydrogens on our reactant side. And then we're done. We have it all balanced now. Does anyone need more time copying it down?
Yes.
And then of course you could go back and put the phases if you wanted to. So it's easier to do this without the phases and then put the phases in at the end. And I would be okay with that.
I finished copying.
Okay, anyone else need more time? Okay, onward. Okay, so that was an acidic. Okay, so this one is in basic solution. And I tried to give you a hint, but sometimes the hint is confusing to people, so let's just go through it. So here's our hydrogen peroxide. Here's the permanganate. Here's oxygen. And here's the manganese dioxide. We're going to start with this. So we start with our ascending oxidation numbers. And we find that our change is in the peroxide, going to oxygen gas is a different oxidation number. And the other change is the Mn. The manganese ion went from +7 to +4. So then we show our half reactions. We have a -2 on this side for the peroxide. So that's how we decide to put the 2 electrons here. From our definition, the electrons on the product side, oxidation is loss. And then our reducing agent is the peroxide. The manganese +7 goes to a manganese +4. We're going to aim for a +4 on both sides. So we put the 3 electrons here from our definition. The electrons as a reactant is reduction is gain. So our oxidizing agent specifically is the manganese +7. We're going to next balance our electrons. So we multiply this by 3 to get 6 electrons. We multiply this by 2 to get 6 electrons. And then what you're going to do next is the distributive property and add everything up. So go ahead and do that, and then I'll show you the answer. Okay, so this is what you should have gotten. And now we have some numbers. And our electrons are 6 on both sides. We have to leave the peroxide together because that's what peroxide looks like. Peroxide is O2 minus 2. You must leave it together. It's like a little pair of twins, or actually it's twins. Like, yeah. Okay, so now we have a few more steps. We're going to insert the coefficients into our original equation. And this was our original equation. Okay, so let's take a look at what we have as far as the oxygens. Okay, we've got 3 times 2, that gives us 6. 2 times 4, that gives us 8. So we have 14 oxygens on our reactant side. We've got 3 times 2, which gives us 6, plus 2 times 2, that gives us 4. We have 10 oxygens on our product side. Okay, so we need to fix the number of oxygens, and we will add water to the products.
So do we add 4 H2O?
Let's just take it one step at a time.
We add 4
No, I said let's just
H2O.
take it one step at a
Oh.
time. Let's not go crazy. Does anyone need more time copying this down? He might be right, but anyway. Yeah, I think he's right. Does anyone need more time? Yeah, we need more. Yeah. Yes. So yes, you were right. Okay, so let's just take a look at the O's. Okay, so we had the 14 here and he was right. We add 4 waters because now we've added 4 oxygens. And now we've got a total of 14. So our oxygens are okay. And now we need to fix the H's. Okay, so we're going to balance the hydrogens by adding H plus to the reactants. So that's over here. We added 2. So then we have 3 times 2, which is our 6, plus 2. Now we have 8. And we have 4 times 2, we have 8. So this is what we have so far. So then we have to consider the question said this is in basic solution. So we need to take care of that. We're going to look at how many H pluses we have, and that will tell us how many hydroxides we can add. And if we add them to both sides, this is like mathematically, you're not changing anything because that's some kind of math something. So we see that we have 2 hydrogen ions, but this is supposed to be in basic solution. And so we will add 2 hydroxides to both sides. And we got the 2 hydroxides because we knew we had 2 H pluses.
So depending on how many H pluses
Yes.
we have, we add the
Exactly.
OH.
Yes. So that's how we get the hydroxides. And it's because of the H plus, and I couldn't fit this all in one line. So I'll just show you the first part. I'll just show you the reactants. So then when we put the hydroxides, here's our products. So it looks like that. Okay, so let's have some student participation and type in the chat what that is. No one's chatting. I have faith in you. What is that? Type it in the chat. You get to participate now, you get to chat now. How come the chat is not lighting up? Oh, it was, I just didn't look at, oh. Okay, well, you're having some spilling issues. Yes, exactly. It's water. Guess I don't know how to look at the chat very well still. Okay. So now it's water. We don't write it as 2H plus and 2 hydroxides. It's 2 water. So now we can write the reactants again, but we will write the 2 water. And then we have the product side already. And now we just need to cancel the water on 2 waters on both sides. Okay, so try to do that on your own. Cancel the 2 waters on both sides and write what you're left with. And then you can go back and put in all the phases. And we just balanced in basic. So just more steps. Okay, so we would just go back and we would just now put all our phases in. I didn't because I was like running out of room trying to cram this whole equation onto my page here because I write big. And we have spectator ions that we don't care about. So typically when we're doing these electrochem, the redox, we just ignore the spectator ions. Ooh, what is that? Okay, I'm just talking to myself. Okay, does anyone need more time copying that down? Okay. So let us go to our module. Okay. Okay. Okay, so let's try to reinforce this with some little videos.
How does a battery provide electricity to operate portable devices? Why does a cut avocado turn brown or metal rust underwater? These processes are driven by specific types of chemical reactions involving electron transfer from one atom to another. The atom losing electrons is oxidized, while the atom gaining electrons is reduced. These reactions are called oxidation reduction or redox reactions, and are characterized by changes in the oxidation state for one or more reactants. The interaction between magnesium and concentrated hydrochloric acid is an example of a redox reaction. Here, magnesium is oxidized to magnesium 2+ ions, and the protons are reduced to hydrogen gas. Simple chemical equations can be easily balanced. However, as most redox equations are complex, the number of electrons lost and gained must be justified. When balancing redox equations, it is essential to observe the law of conservation of mass. Each element's amount and any gain or loss of electrons must be balanced on both sides of the reaction. Thus, if one reactant is reduced, another must be oxidized. The method of half reactions is used to balance redox equations successfully. Consider the reaction of permanganate with oxalate. For aqueous acidic solutions, assign the oxidation states and divide the reaction into its component half reactions. Then balance each half reaction, omitting hydrogen and oxygen. Here, manganese is already balanced, but the oxalate needs a coefficient of 2. Secondly, balance oxygen atoms with the addition of water molecules. And thirdly, balance hydrogen atoms by adding protons where required. Balance the charges by adding electrons. Since manganese is reduced, 5 electrons are added on the reactant side. Conversely, oxalate is oxidized, thus 2 electrons are added on the product side. Multiply the half reactions by an integer so the number of electrons added is equal. Lastly, add and simplify the balanced half reactions by canceling out species on both sides to obtain a balanced redox reaction. For basic aqueous solutions, the procedure is similar but includes one additional step. Here, an equal number of hydroxyl ions is added to both sides of the reaction to neutralize the protons before summating the balanced half reactions.
Okay, so that's basically that's what we did. They just combined the steps. Okay, and then let's go ahead and look at this one. It's also very short. Oh God, what's happening? Oh, I didn't start. My bad.
When electrons flow through a wire or ions flow through a solution, they generate electricity. This flow of electrons, or more specifically, electric charge, is defined as an electric current. But what causes the electrons to flow? Consider a redox reaction between copper and zinc. When a zinc electrode is placed into a copper ion solution, electrons are transferred from one substance to another. Zinc, having a greater tendency to lose electrons, is oxidized to zinc ions, while copper ions are reduced to solid copper. In this reaction, electrons flow from zinc to copper, but this reaction does not generate electricity. Now, consider that the reactants, zinc and copper, are physically separated and connected via an external conductor such as a wire. The reactant's tendency to gain or lose electrons still persists. driving the electrons to flow through the wire which connects the two half reactions. This electron flow constitutes an electrical current and can power electrical appliances such as a light bulb. Electrical current is measured in amperes. 1 ampere equals the flow of 1 coulomb of electrical charge per second, corresponding to 6.24 times 10 to the 18th power of electrons per second. The flow of electrical current is similar to water flowing down a waterfall. The water is driven by the difference in gravitational potential energy, while the flow of electrons is driven by the difference of the electrical potential energy between the reactants. The difference in electrical potential energy is described by the terms potential difference, electromotive force, or cell potential. The cell potential is a measure of the driving force between two reactants and the tendency for electron transfer. The cell potential of two isolated reactants is measured with a voltmeter, which is read in cell voltage. 1 volt correlates to 1 joule of potential energy per 1 coulomb of electrical charge. A high cell potential indicates a large driving force and greater ease of electron transfer. Lastly, the cell potential or electromotive force depends on the reactant's nature, reaction temperature, and the concentration of ions present in the reaction.
Okay, so now let's go back to our notes. Okay, so here we go. Okay. Okay, so now we have a lot of definitions. These are really good for multiple choice questions. Hint, hint. Okay, so there's a lot of terms that we need to look at. Okay, so we're going to start with electrochemical cell, a system consisting of electrodes that dip into an electrolyte, and in which a chemical reaction either uses or generates an electric current. This is used interchangeably, Voltaic or galvanic. You want to be familiar with both terms because half the time Voltaic is used and half the time galvanic is used. But it's an electrochemical cell in which a spontaneous reaction, so that's the key here. Spontaneous reaction generates an electric current. So spontaneous and generates, the two key terms here. So this is a different term, the electrolytic cell. So you're using an electric current to drive an otherwise non-spontaneous reaction. So this is completely different.
Professor,
Mm-hmm.
for number 3, the one you just did, would you
Mhm.
say that that could be like a light bulb, or
No,
that's passive? Oh, that's right, because it goes from
No.
positive to negative.
no.
So what's an example of that then?
Oh, we're going to do examples.
Oh,
Yes, we will be doing examples. Right now, we just want to look at the terms.
okay.
So you look at the difference in the definition. So right now, just kind of familiarize yourself with the terms and you see the difference in the definitions. In the electrolytic cell, you're using an electric current. So you have a source of electricity to force a reaction to occur. The electricity is a form of energy. So it's completely different. You're providing energy to make the reaction go. And the energy is in the form of electric current. Whereas this one, this one was in the video. And we're gonna look at both of these. The half cell is a specific half reaction. The salt bridge, you have the electrolyte, it can be a gel or aqueous, that's not critical. And you use it between the two half cells, which are beakers typically. And it allows the flow of ions, but prevents the mixing of the solutions. Ooh, I forgot, you guys have books. So if anyone has a physical book, let's see. Or maybe you could look at the ebook. Oh, okay. Okay, so if you can open up your ebook, or if you have the physical book, and then you want to look at, let's put it there, figure 18.1. So if you actually have a textbook, you could pull out your actual textbook and you could look at figure 18.1, and it's a galvanic cell. Or if you can pull up your ebook side by side, that would be good. Okay, so we did all of those half reactions and we were able to therefore label them. And it's important because if you look at this, it's called an anode, but specifically the anode is the oxidation half reaction. Whereas the cathode is the reduction half reaction. So you need to know your oxidation and your reduction because you're going to match the anode with the oxidation. This is always. And the cathode always with the reduction. So that's always. And then we saw in the video the cell voltage, that's reading volts. It measures the difference in electrical potential between the anode and the cathode, also known as electromotive force, also known as cell potential. You need to know all those terms because they're all used interchangeably. Ooh. Hopefully you have your figure 18.1 in your book because this would be a question. So the voltaic, so the question is asking you to draw a voltaic cell from a half cell. You've got cadmium in cadmium nitrate. You've got silver and silver nitrate. You have a salt bridge. It's telling you the silver ion is reduced, and you're asked to draw the cell, label the anode cathode, show the corresponding half reactions of this electrodes, indicate the electron flow in the external circuit, the signs of the electrodes, the junction of the cation, blah, blah, blah. Okay. Okay, you would start by showing your half reactions. You'd have to look at this problem and figure out the half reaction. So that's how you would start. And then you go back to your definitions and you would label the anode for the oxidation and the cathode for the reduction. So that's how you would start. Okay, so then you'd have to look at the half reactions and realize the cadmium is giving off electrons and the silver is accepting electrons. And so the electrons flow from the cadmium to the silver. Yeah. And so let's see if I can make this diagram bigger. I know I can. I just gotta do my little clicky thing. Okay, so go here. And let's see if this helps. Okay. If I make it big, well, okay, can you guys see that well enough? This is the diagram. This is it. It's all labeled and everything.
I think I can see it. Okay.
Yeah, if I make it any bigger, then the words get, like you can't read the words very well. Okay, so this is the answer. This would be the answer to the question. So let me give you some time to copy it down, and then we'll go over it.
Professor,
Mhm.
is the salt bridge labeled KCl?
Yeah, this one is potassium chloride. It could be potassium anything. It could be sodium anything. It's typically either potassium or a salt or a sodium salt, because those are cheap. Yeah, you could just take sodium chloride and make a gel out of it, or you can make a solution out of it. Because what's happening, see, when the cadmium is giving off electrons, it's building up cadmium ion. And if we don't take care of that buildup, then it's going to be more difficult for the cadmium to continue to give up electrons. And so we have this salt bridge that the ions can go through so that we don't have a buildup of cadmium ions. So the cadmium ions can go up here, and then we can continue going this way. It's just the idea of Le Chatelier. If you have too much of this, you won't be able to keep going towards product. We want the cadmium to give off electrons, because look what the silver wants to do. The silver wants to gain electrons. So it's technically this piece of metal, silver, would be gaining the electrons. Or actually, I'm sorry, the ions would be gaining the electrons. And then what would happen is the silver ion here and the silver solution would gain electrons, and then you would start to see crystals of the silver forming on here. I guess blue on blue is not that good of a color. Okay, so silver solid would start to form on here, because the silver ions are gaining electrons and becoming silver solid. This is solid. That's an S. Oh my God, that just looks like a blob. Okay, so we're forming silver solid because it all goes back to these half reactions. If you know the half reactions, then you can see what's happening in the whole system. The silver ions are going to silver solids. You get crystals forming here. What's happening to the cadmium solid? It's going to cadmium ions. So you are technically losing. You're eating away here. You're going to lose the cadmium. Ooh.
Professor,
Yes.
does it says voltmeter car light?
Or light.
Wait, or light?
Yeah. Okay, so if you have a voltmeter, that will register the electrons, that will register the current. Or if you had a system where you had a light bulb here, like you had this attached to a light bulb. Okay, that's starting to look weird. Okay, light bulb. Let's make it go straight across. Okay, so this is, okay, so remember back in the day when you had light bulbs? Okay, the electrons are flowing through the wire. This is a piece of wire connecting these metals. You could have the wire clipped onto a light bulb. There's a way to do it. And then if you've got the current going through, you would see the light bulb going off. You would see the light. So you could set up a system like this, and you could either have a voltmeter, which would register the electrons going through, or the electrons could go through the light bulb, and then they would make light. You would have the electrical energy being transformed into light energy. So it says voltmeter or light. And then the question was saying to show the flow of electrons. That's again back to your half reactions. Cadmium is losing, so that's why this flow of electrons is going away from the cadmium. So that's how you would know what the electron flow is. And again, back to your half reaction, you see that the silver cathode is taking the electrons, and that's how you know the flow goes towards the silver. So this is explained pretty much from the half reactions and our definitions and understanding what's happening here. You get the half reactions correct, and then everything else just falls into place.
Professor.
Yes.
So then, I thought before you showed us this that when the ions of a cation or cadmium like break off, basically cadmium ions would be flowing through the wire and come to the silver.
No,
the
the
case.
wire is for the electrons.
Right. So
The
those
cadmium would go up here.
Yeah.
The cadmium ions would go through your salt bridge. The salt
Okay.
bridge is for the ions. The wire is for the electrons.
I see. The ions give off the push or the nudge for the oxidate or the electrons to move.
No, the electromotive force.
Right.
Remember in the little video, it said, oh, there's this electromotive force.
Mm-hmm.
Okay, so to answer your question, the answer to your question is that cadmium wants to give off electrons and silver wants to gain electrons.
Mm-hmm.
So if you have a situation where you have a metal that really likes to give off electrons and a metal that likes to gain electrons, and this is going to work. That's the idea. You want to be very careful in what you chose. And you would specifically want a system where you choose a metal that loves to give off electrons and combine it with a metal that loves to gain electrons.
So then, where would the ions go? Would they just stay in the salt bridge, or did they go
No,
all the way across?
they could go all the way across, and they could go in here. Because see, this is losing positive. It's all about the positive charge. This is losing positive charge.
Mm-hmm.
So if you had positive charge going in here, and you're losing positive charge.
It allows the electrons to keep moving through.
Yes, exactly.
So that basically serves as, like, in biology terms, it maintains the electrochemical gradient to allow.
Yes,
the
it
electrons to
does.
keep
It
cycling.
does. Yeah.
Oh, that
Yep,
makes
yep,
sense.
yep. Yeah, because if you build up too much positive, you get a positive gradient and you can't push against it.
Right, not without a lot of force or energy.
Yeah, it would stop.
Mm-hmm.
But that's what the salt bridge is for. So typically in the laboratory, when we do this, we have glass tubing that's bent like this, and then you have to put the solution in. We use sodium chloride, And then you put little cotton plugs in here.
Hmm.
And so, and we have voltmeters, so you could measure this.
Hmm.
So yeah,
So
this
then-
is
yeah.
the system all is explained from the half reactions.
Mhm.
So it does make sense.
Yeah. Just so then what purpose does the potassium chloride serve? Does it just funnel along the
You
the
would want
ions?
to have something in here that has some ions in case you need to balance the ions on either side.
Oh, okay. So it doesn't like allow for the cadmium ions to move quicker or anything like that?
I don't know about the rate. It's more about that we need to get rid of these. And so
Right.
we typically have a salt solution. It's just a
Mhm.
low concentration of the salt.
Okay. Okay.
Does anyone need more time copying this down? I think I have to go back to my other size. Otherwise, it's going to be too big. Let's go back to 100. Okay. So what we're going to do now, because we've been sitting here for over an hour, is we can go ahead and take a little break. And then we'll come back to this. I'll pause the recording if I can find it. Okay, so we are back to our lecture notes. And we're going to learn a shorthand notation. So this is essentially for the chemist shorthand. Okay, so you always put the anode first, and then the double line represents the salt bridge, and then you put the cathode. So for example, the Voltaic cell that was on the prior page, we would write the anode this way, cadmium solid, and we will put the phases in. Went to cadmium +2, and that was AQ. And then we draw the double lines to represent the salt bridge between the two half reactions. And then our cathode was the silver, which was AQ, and it was going to silver solid. So this is what we just did. The diagram you copied down. So this would be the shorthand notation. For our previous diagram. So then if you were given a shorthand notation, you should be able to, from the shorthand notation, write the half reactions and then balance the electrons and then write the whole reaction. So the problem would give you this. And from this, you would have to do your half reactions. And remember, we're always going to do the anode first and then the cathode. So this would be the anode. So you would go from the solid to the ion, and then you notice there's a +1 here, and you would need 1 electron. And then here's our cathode. So we have the tin 2 going to tin has a 0 charge. And so we would want a 0 on both sides. And that's how we would know to put the 2 electrons. And from these 2 electrons, we would know to put the 2 here. And then we do distributive property and add everything up.
Professor, is that TL?
TL. That is thallium. And then what we could also do is give concentrations, give pressure. So for example, we would put what the molarity is and what the molarity is. And then we would know the conditions of the cell. So this would be including the molarities. And then specifically a hydrogen electrode looks like this. It uses a platinum wire and the hydrogen ion with hydrogen gas and then the platinum wire. So this is just it, the notation for the hydrogen electrode. And the platinum is expensive, and that's why one of the reasons you don't want to break this. Okay, the electromotive force was explained in the video. And so work is needed to move electrons in a wire. And this is what the video was explaining, that an electric charge moves from a point of a high electric potential or high electrical pressure, you can think of it that way, to a point of low electrical potential, or you can think of it as low electrical pressure. And so think of it as like water pressure. So the difference in the electrical potential is called potential difference, which makes sense. And the units are volts. So V for volts. Okay, now we have a little equation. Electrical work equals charge times potential difference. And here's the units, and you absolutely must use these units. So for electrical work, we will use the units of joules. For charge, we'll use the units of coulombs. For potential difference, we will use the units of volts. And now we have a constant called Faraday's constant. And yes, that's like a real person. You don't need to know the dates or anything else. That's interesting. He worked a lot on electric motors. Oh, look, when he did that, we could have been using electric motors in cars like 100 years ago. But why didn't we? That's a whole story in itself. Yeah, we could have had electric cars like, anyway. You have the electric motor in the 1800s. Okay, so I would not ask you about Michael Faraday, but you're going to want to have that constant written down so that if you need to use it, you will have the number. Okay, does anyone need more time copying this down?
Yes.
No problem, I'll continue to pet Mucal. Okay, so you can just put in the chat when you're done. Yes, electricity is electrons. Yes. What? Oh. You guys use electricity like so much. Oh, okay, are you done? Yeah, just make sure you get everything written down because your brains are probably getting full at this point. So make sure you just copied it down correctly. That's really all that we're aiming for at this point because we're covering a lot. Okay, so does anyone need more time?
30 more seconds.
Oh, okay. No problem. Okay, we good?
Also, Professor,
Yes.
the 96,500 coulombs is F?
Yeah, that's the Faraday constant.
Oh, okay.
So you're going to want to have this on your cheat sheet because I typically do not put it in the question. I mean, I might, let's say, for example, I ask a question and you have to use this equation. Or actually, we're going to have an equation coming up where we have to use it. We'll get there. We haven't gotten to that equation yet. I'm ahead of I'm ahead of myself. This is just telling you that 1 mole of electrons has this many coulombs. And we do have an equation coming up where we will use this Faraday's constant. So you would want this on your cheat sheet for sure. This is just telling you how to get electrical work if you know the coulombs and you know the charge, the volts. But we do have a formula coming up where an equation where we have to use the Faraday's constant. So you want to make sure you have that on your cheat sheet. Okay, so now we look at our little equation here, and it's work equals minus F times potential difference. And we're saying that the voltaic cell loses energy because it does work on the surroundings. So that's why we have the minus. So we're going to abbreviate electromotive force as EMF, or typically what most books tend to do and your lab manual does is we call the electromotive force E of cell. So now we have an equation to calculate the maximum amount of work if we know the number of electrons. And then here's our Faraday's constant. And then we would also want to know the E of the cell. Okay, so the problem that we're given here is the shorthand notation. And then here's our electromotive force, that's volts. And we're asked to calculate the maximum electrical work. So we're trying to calculate this. So what is this? And we're given 5 grams. So we would start by taking our shorthand notation that we just learned, and we would want to write the half reactions from it. And so I did this one first. So here's my mercury ion. This is mercury 1 ion. And then because there was a 2 here, I had to myself put in the 2 here. I know my mercury is a 0 because it's uncombined with another element. And so I want 0 on both sides. So I figure if this is a +2 and I add 2 electrons, then this will give me a 0 on this side. And so I'm good. So I'm balancing my half reaction. Then I look at my other half reaction, and that was hydrogen gas. And I know because there's 2 here, I had to on my own put the 2 here. And this one also is just a coincidence. This one also we want a 0 on both sides. Because this is a diatomic, it has a 0 oxidation number. So 2 plus, 2 minus, 0. So we had to do all of this so we could get our N. This. So now we know that the N is 2.
Professor, so
Yes.
the question would specify which species it wants the moles.
Oh, we
Like-
have to make the electrons the same. So remember how we balanced electrons when we did our half reactions?
Yeah.
We have to have these electrons the same as these electrons.
Oh, so the
This
electrons would
one-
just.
Yeah, this one, in this particular case, they ended up being the same. But you might have an additional step where you would have to multiply one of them to get them the same, like some number. And that would be your electrons, and that would be your N.
Oh, Professor, it's like the delta G equation in our lab.
What?
This equation similar to the one that we have in delta or in our lab, right? That has like delta G, and you're calculating like the potential, I think, energy.
Yeah, yes, there might be a relationship between what we're doing and your laboratory. Okay, but to answer his question, you could have an additional step where you have to multiply by some number, and then you would know your number of electrons. In this particular case, they ended up being already the same. Yes, there is a relationship between what we're doing and your laboratory. Okay, so now we have our little equation that we're going to use. And we have everything we need because the problem itself had given us the volts. So we go back to the problem and we see that they gave us the electromotive force, they gave us the volts. So we had that. That goes in here. And then the Faraday's constant, you were supposed to put in your cheat sheet, so that goes here. And then we just got the N from doing our half reactions, and so that goes here. And then we just plug everything in. Okay, so go ahead and pull out your calculators and do this all on your own. And that's what you should have gotten. And then you have to take your units and fix them to joules. So you have to know that 1 coulomb times a volt is a joule, and then you just change the units to joules. Okay, we're not even done though because we didn't consider the 5 grams. We get to use our dimensional analysis skills. This is joules per mole of hydrogen, and for 1 mole of hydrogen gas is 2.02 grams, and multiplied by grams. And what happens to our units here? Okay, so our moles of hydrogen cancel with our moles of hydrogen. The grams of hydrogen cancel with the grams of hydrogen, and the grams of hydrogen was given in the problem. And then we have the final answer. Yeah, let's not worry about sig figs in the lecture. Does anyone need more time copying it down? Okay. Okay, so now looking at standard cell EMFs and standard cell electropotential. So a cell EMF is a measure of the driving force of the cell reaction. The cell EMF depends on the ability of the oxygen half reaction to lose. This is what he was asking already, about how you figure out what's happening. So this electromotive force is how much does one of the elements want to lose electrons, and how much does the other element want to gain electrons. So the way that we get the E of cell is by taking the oxidation potential and adding the reduction potential. So the reduction potential is a measure of the tendency for an oxidation species to gain electrons. So typically we look at reduction potentials. There's a table in your book, table 18.1. It takes up the whole page, and it's the standard reduction potentials. And then the electropotential is an intensive property. Oopsie. Okay. Okay, so what this means for us is that we would multiply the half reactions, but we leave the volts alone. So that's what it means for us. So when we are balancing the electrons and we multiply the half reactions, we leave the volts alone. That's the idea of an intensive property. When we use this little 0 superscript, we're defining our standard state conditions: 1 molarity, 1 atmosphere, 25 degrees C. So we would use that little e with the superscript 0 for our standard state conditions. Okay, so if we look at table 18.1, we would see that fluorine is the strongest oxidizing agent. The fluorine really wants to gain electrons. It has a positive 2.87. That's considered a very high number. So this is referencing your table 18.1 in your book, if you have your book open. So the way this works, the best oxidizing agents are easily reduced. That's a always. Okay, go back and look at the table. And if we're looking at this table, we would see the strongest reducing agent is lithium. The lithium's on the bottom. And the best reducing agents are those found at the bottom of the table. So we're taking what's at the bottom of the table and we're flipping it. So I'm looking at the table and I had to get my lithium solid, I had to flip it from the table. I want to look at the lithium as a reducing agent. In order to do that, I have to flip what I've got on the table. And then when I do that, I have to change the sign of the volts. So I want to look at lithium solid. I look at the table, I see that according to the table, I need to reverse what's on the table so that I can look at it as a reducing agent. When I do that, I have to change the sign of what's on the table. And we know that a plus volt is good. And so this shows you this plus 3.05 volts. That shows you lithium solid really wants to go to lithium ion, like a lot. Oops, okay. Did anyone need more time copying that down? Okay, then we have a little problem. It's asking us to put the oxidizing agents in order. So chlorine gas, hydrogen peroxide, ferric ion. So we're going to start by writing the reactions as reductions, because if these are reductions, then these are all oxidizing agents. So we'll start by doing that. I'll give you some time to copy it down. So this would be all of these as oxidizing agents. This would be a plus 3. So these are all volts. Looks kind of a little funky. And once we get the volts, we just look at those. And that's how we can put these in order. So you would need to have this table to do the problem, or I would have to give you the volts. Okay, the next question is asking about reducing agents. And so this is telling you that you look at the table, and in order to make these as reducing agents, you need to reverse the half reactions and change the sign of the volts. And then you can look at the volts and put them in order. So go ahead and put the reducing agents in order from lowest strength to highest strength. And so this is the answer that you would get. So if we look at aluminum, it really wants to give off electrons. It's like, yes, that's considered a high number. Okay, so now this is how I solve the problems, and please note it is different from your book, but I like doing it this way. So I set up the half reactions. I flip the one that I need to, and if you flip it, you have to change the sign of the volts. So I'm using the table from your book, the table 18.1 from your book. And I'm using I know the definitions for cadmium as an anode and silver as a cathode. I use the table I had to flip one of them. In this case, I had to flip the cadmium. And then the reason I like doing this is to me, it's very straightforward because now all I do is I manipulate the half reactions and then I just add everything up. I don't have to do anything fancy. I just add up the half reactions and I add up the volts. And this is what you're doing in your worksheet experiment this week. So again, this is how I do it. It's different than your book because this to me makes more sense.
Professor, what do
Yes.
the 2 plus signs do?
Oh, okay. So the way that I do this is I look at that table in your book and then I'm just going to add up my half reactions. Let me see if I can box this. Okay, so I'm going to add up my half reactions. And then I can get the overall. And then separately, I will add up my volts. And now I have my volts for my answer. So this is how I do the problem. Your book does it very differently. But to me, this is very straightforward. This one was as is from that table. This one I had to flip. I knew if I had to flip it, I had to change whatever the volts was from the table. And then once I do that, I just add my half reactions and that's how I get my overall. And I just add my volts. And this is how I always do the problem. I've seen students make mistakes when they do it the way the book shows it because they put the sequence wrong. It's like, this one is to me kind of foolproof that I'm not going to mess this up because I know one of them will be as is from the table and I will have to flip the other. But when I flip the other, I'm very careful on the volts. I change whatever sign it is on the volts.
Oh, so Professor, so we just make it like all positive for the
That's
volts.
the idea. Yeah, if you didn't know what to do, you could try it different ways to get the highest positive volts. So in other words, if they didn't tell you the anode and the cathode, if they just said, like, you've got cadmium solid, you've got silver solid, just give me the best volts, then you would want to manipulate one of them so you get the highest volts. Because that's always good. A positive volt is good. Because they may not always tell you in the problem which one's the anode and which one's the cathode. And it doesn't take that long to go through the possibilities. You'll see pretty fast which one to flip to get the positive volts. So I like doing it this way. This way makes more sense to me. It's like, I know what steps to do. Does anyone need more time copying this down? Another way to ask the question is to give you the shorthand notation. Okay, so this was the shorthand notation. So you have to recognize from the shorthand notation what to do. So it's pretty much telling you aluminum solid, go to aluminum +3. You look on the table and you had to reverse it. And then that's how you had to reverse, change the sign. So you get this from the table by reversing it. It's telling you the iron +2 is going to iron solid. And you're using this as is from the table. And then you add these up. And you add these up. And that's how you get the overall answer. Number 3 is an example where it's not really telling you as much information. It's like, it's not telling you which one to do. You have to, on your own, figure out which one to flip. So you have to look at the different possibilities. It's giving you everything, but not telling you a shorthand notation and not telling you the anode and the cathode. So what you would do is try different possibilities until you get the highest number for the volts. So it turned out for this one that you would use the manganese as is, but you would have to flip the iron +2. And then from the table, you had to change the sign. And then you add up, oh yeah, multiply by 2 because we need the electrons the same. Multiply by 5, but this is an intensive property, so leave the volts alone. Add up all the equations, add up the volts, and then there's your answer.
Professor, for number 2,
Mhm.
why don't we flip the sign for the 0.44 volts?
Oh, okay, so, okay, let me get my book out. That one was as is. So let me go to table 18.1. I thought I had a table someplace and on my gazillion. I don't even know where it is. No. I had a table someplace. Oh, wait, it's in your, wait a second. I have an idea. Ooh. And it's in here. Okay, let me find it. Let me show you. That will be easier. Okay. Okay, so we need to go to the table. It is in your Marav. It's also in your textbook. Okay. Ah, here we go. Okay, so we're going to be looking at this and we're always going to have to flip one of them. So usually the way this is going to work is if you see a negative, that's the one you're going to want to flip. Because if you flip it, then you have a positive and now you get to add a positive to a positive. We want positive volts. That's the way the volts work. So we would use this table and we would find each of our half reactions and we would want to make sure we flip one of them. This table looks like this is incomplete.
Oh, I think I kind of get it now. So that means if we flip the 1.66, it'll become 2 negative. So we
Oh,
have to
right.
flip the 0.44.
Yeah, so are you looking at number 2?
Yeah.
Okay. So let me, okay, so this one is on your table. This is in the table 18.1. Fe plus 2 is going to iron solid. Okay, so this one got used as is. This one, I multiplied it by 3, but I leave the volts alone because it's an intensity property. So I use this one as is, and I left it as a negative 0.44 volts because I used it as is. But the aluminum, I go down to the aluminum and I see that on the table, the aluminum's in the wrong place. I need to flip the aluminum. I need to reverse the aluminum. And when I reverse the aluminum, I change the sign, and that's how I get this very nice positive volts. And then when I add up my volts, I end up getting, I still get a positive overall, which is good. I'm always going to flip one of them. And probably the best way to do this is just go ahead and flip one, add up your volts, and if it ends up being negative, then you flip the wrong one. You can just do that on scratch paper really fast. You definitely will have to flip one of them. And then you want to aim for a positive when you get all the volts added up. That's supposed to be a positive, so it's kind of like a, yeah. So this is how I do it. If you want to do it the way in the book, I don't care. But I'm just going to show you this way. This way to me makes the most sense because I know I got to flip one of them and I'm aiming for positive. Oh yeah, so what I'll do is okay, and this is what we're doing today. We're done. What I'll do is I'll put this on my YouTube channel and I'll put the date. Okay, so this is enough for today for your neurons. I don't know if your neurons could, yeah, this is plenty. And plus it helps us with your worksheet for your lab, because this is exactly what we're doing in lab. So if I was in lab and I said, and I wanted to predict my observation, I would predict that the aluminum solid would they disappear or dissolve. And I would have a precipitate of iron. So that's what I would predict from based on my net ionic equation. Okay, does anyone need more time on this? Because we're done. You got plenty to do. We're done for the day.
So Professor, you'll put this recording on YouTube?
Yes, my YouTube channel. You got my YouTube channel that I have. I will put it on that with today's date.